our goal in this video is to understand Euler's method to the extent to where we can actually program it now. And we're going to do this by looking at a differential equation that's called the logistic growth model. Okay, and even before that, let's see, what's the scenario that we're going to be thinking about as we try and use this logistic growth model. So, what we have is this population of deer, and at this current point in time, there's 900,000 of them. And we have this number R, which gives us an idea of how quickly this population is growing, and that number is 0.2311. Some of you might remember how to find that if you took differential equations. Okay, but here it's just going to be given to us. And the carrying capacity we have is 1,072,764. Okay, and the carrying capacity, that's just really the maximum number of deer that we expect in this habitat. Okay, so in other words, if we have less deer than this, we expect the population to be increasing, and if there actually happen to be more deer than, if the number of deer exceeds the carrying capacity, we would actually expect a die-off. Okay. So next thing here, we do have Euler's method. I have written right here. And I also have the differential equation that we want right here. Okay, this is highlighted here. This is the logistic growth model. Okay, but you might notice here that there are P's and T's and not Y's and T's. So it might be a little less confusing if maybe I change some of these Y's to P's, because that is going to be the variable we want here. I think that'll help a little bit. Okay. And then let's move down here a little bit. Okay. So let's change that. So if we're going to do this over a 3-year period, then what we're going to say is we're going to be thinking about an interval of length 3. Okay. And we're going to be splitting this interval up into pieces, and the question is what is our step size? Okay. In what manner are we going to be splitting this up? And so I want us to start off with 0.25, but we'll decrease this step size and kind of see what happens. But let's just start off with 0.25 to keep it maybe simple here in the beginning. Okay. And now what we want to do is start writing the code that we need here. But I think we should start off with some of our knowns. Like for instance, you do see that h there is 0.25. We might as well include it here. We were given some other constants and stuff up here, like k. I'm going to just go ahead and copy and paste that. Okay, and let me also move this. There we go. So there's k, but I don't want these commas in here. I keep deleting the wrong things here. So we have k equals, there we go. Okay. And let's see if we have anything else up here that might be important. I think R, we're going to want that. Okay. And is there anything else? I think it might also be helpful to consider our initial deer population of 900,000. Okay. And so I'm going to tell you what we're going to do here. We're going to create a matrix P, and the first column is going to just be the year. Okay. So it'll start off with year 0, and then the next spot in our matrix will be 0.25, and then the next spot would be 0.5, and so on until we hit year 3. And on the other side of this, we're also going to be thinking about the population as the time changes. Okay, and so that'll be our second column. So let's just go ahead and say, hey, our first row, first column entry should just be 0, year 0. Okay. And our first row, second column should be that initial population. And let's say that that initial population, again, is 900,000. Okay. And we can suppress all this stuff. Okay. And then next, we want a for loop. Okay. And the question here is, you know, how many times do we want this to, you know, repeat itself? And if we were to think maybe for a second about maybe just an interval of length 1, right? Interval of length 1 that we split into 2 pieces. Okay. If we were to, or maybe a step size of 0.5. Okay. If we were to do that, it would take us 1 calculation to get to 0.5, and then it would take us 1 more calculation to get to 1. Okay. And we're going to have a similar thing here if maybe now let's think about an interval of length 1. And if we let h be 0.25, how many calculations will it take us to get to 1? Well, it'd take us 1 calculation to get to 0.25, 1 to get to 0.5, another one to 0.75, and then a fourth to get to the last one. Okay. So this is actually just as simple as taking the step size and multiplying by the length of the interval. So for us, our step size is 0.25, the interval length is 3. If we I should reword that. If we were to think about our step size as being 0.25, it means we've kind of split the interval into 4 pieces. So I'd want to take that 4 and multiply by 3. Okay. So we'll have 12 calculations. Okay. And again, if it was of length 1, we would have had 4 calculations. Okay. All right, so there's that. And let's actually start off with the easier piece here. I left a little gap because I'm going to do the population above this because that's kind of the more important calculation. But let's just think about that first column. Okay. So I'm going to leave this section here blank for a moment, the row. Okay. But we're going to be in the first column there, right? Okay, so good. And then every time we run this, right, we want the row to go down 1. Okay, we want it to go down 1. Or another way to say that is we're starting off, right, in row 1, and then we go to row 2, and then to row 3, and then to row 4, and so on. Okay. So I'm going to say I plus 1 here, and P, or is equal to P of I comma 1. Okay. And again, notice that that comma 1 in both of these, right, is saying that we're only thinking about the first column here. We are changing the row, but not the column. Okay. And every time we do this, we want to increase by 0.25, because that was our step size. Or how about we'll just leave it as h. Okay. And we can actually test this out, make sure it's working properly. Okay. But the idea is here is the very first iteration of this. We would be plugging in I equals 1. So we'd take P of 1 comma 1 and add 0.25 to that. And remember, P of 1 comma 1 was just 0, so this is 0 plus 0.25. So now that tells us that the second entry is now going to be 0.25. And if we do this again, we'll add another 0.25 and so on. Okay, and I just need an end here. So let's see how we've done. Okay. The program might get a little upset with us because we actually don't have everything else filled in for the second column, but we'll try it and see what happens. It might give us an error. Okay. So it didn't, so that's good. Okay. And you can see here on the left, it is increasing by 0.25 until we get to 3. Okay. That's exactly what we wanted it to do. So let's go ahead and click out of this. So that looks good. Now for the hard part, actually implementing Euler's method. And also in terms of the logistic growth model. Okay. So this, I'm going to actually comment in here. Time and population. Just so we know what's going on. And so we'll want to do a similar thing, I plus 1, but this time we're going to be in column 2, is equal to. And if we go up here and look at that little formula, our recursive formula, which maybe I'll just bring this down here a little bit. Let's put it right here, just so we can look at it. So to get our new term, we want to take the previous term, which would be the ith term in the second column, right? Okay. And we'd want to add to it. Okay. And this part over here, this is just saying that you're going to plug in the current or previous, however you want to think about it, time and population. Okay. But if we look up at our differential equation that we have up here, which maybe I should bring that down as well. A little further up. There we go. Yeah, I want both of these to be visible to us. Okay. The part that we're calling f here, when we talk about a differential equation, is we're talking about this right-hand side of the differential equation. Okay. And one thing I want you to notice is there aren't any t's in this. We're only going to have to plug in p. Okay. So that's kind of nice. And so really is what we're saying is we want to use this right here. I'm going to copy and paste it. Because again, that part that I just highlighted, this is f. Okay. But if I try to run this right now, it's going to be a little confused because we haven't defined what p is. P is actually, right, we're creating a vector or a matrix, I should say. So p standing alone is not quite enough. We want to say the previous p. So I comma 2 and I comma 2. Okay. Okay. And so the only difference between the left and the right is this is going to be our new updated version of p, and these are the old ones. That's why it's p of I. P of I. Okay. We can go ahead and suppress this. Now, if I try to run this right now, MATLAB will be upset because whenever we multiply, we have to use the asterisks. Okay. So I need a multiplication symbol there. Okay, so that's fixed. Let's see. This, I think, will take care of things. And let me just make sure I have everything suppressed here. It looks like we do. And I'm just going to go ahead and put a P down here so it displays our matrix P that we've created. Okay. And unfortunately, when it does this, oftentimes it's going to put things in scientific notation. Okay. Which isn't a big deal because maybe we still want to make more calculations so we don't care exactly what these numbers look like. We'll talk about making tables more here in a little bit, but one thing that I do like about making a table out of our data is that it takes it out of that scientific notation. So I'm going to actually say P of, and I want to point out that the first column here I want to be time, so I'll be using the first there, the first column, and here I'll be using the second. And so now the question is well, how do you say you want the entire first column, right? Because if I say wanted the entry in the third row, first column, I'd say this, right? But how do I say I want that whole column? Well, you'll put a colon there. Okay. Colon. And we'll talk about how we can add labels to our table and stuff here in a minute. I just want us to be able to see the data in a little bit easier to look at format. Okay. All right, and there it is. Okay. And I'm realizing, looking at this, that these numbers are not the numbers that I would want. And it's because I'm missing something. Okay. Some of you might have noticed that all I have put here is F. Right? All I put here is F. And if we look up at our recursive formula that we're supposed to be working with, you're supposed to multiply this second part here by the step size h. So I'm going to also add in a times h. Okay, and this should give us a little bit more reasonable numbers here. Okay, so I'm going to run it again. Okay, and so that's looking much more reasonable. Okay, and so it looks like we've made it up to 980,160 deer after this 3-year period. Okay, and is what I want to kind of show you all is I actually pulled this example from somewhere that I found online. I'll post this under modules along with this video. But I want you to see that even with a step size of 0.25, which is actually a pretty large step size, we're not that far off here. Let's go ahead and actually look at the actual number here that we were looking for. Somewhere way down here. Okay. I may have passed it. Okay, so this was the beginning. Where's it at here? Oh, there it is. I scrolled past it twice. It's this 978,830. Okay, and right, we calculated about 980,000, but this is being based off of actually solving the differential equation by hand. Okay, and we haven't had to do that hard work of solving it by hand. You saw there was a lot of work up there, right? Okay. Now, we could change this step size, like I had mentioned, to make this a little bit more accurate. So let's maybe say instead, let's maybe make the step size 0.1, which means that we would be dividing, or we would want to do 10 now, 10 times our interval length. So that's going to be 30 iterations of this algorithm. Okay. And you can see we're closing in on that correct value. And we could go even a little crazier. We could go with 0.01. And so then that would mean we would want to do 100 times our interval length. So that'd give us 300 iterations. And you can see we keep getting closer and closer and closer. And right, this really isn't taking that long to run. Okay, so you know we could keep making that interval smaller and smaller until we're kind of within, until we're happy with the results. Okay, but is what I'm going to want to do in our next video is we're going to plot some of this data. We'll put this data in a table and actually label. Or put headings on the table. Okay. But for now, that's it for programming Euler's formula.